Okay, so here's what, let's just look at what's due this week. And right before Valentine's Day here, and you have homework 5 due tonight. And let's just look ahead. And a week from Monday is our first exam covering chapters 1 through 15. So we'll finish up all the new material somewhere, probably partway through this lecture, we'll have time for a review 1 week from today. So let's get started and let's go over to the document camera. And where did we leave off? Let's just look at the previous page. We left off on page 61, where we were doing confidence intervals. Confidence intervals you make a point estimate for what you think a population parameter is, for example, the population average or the percent, in like a poll, and a political poll, and then we attach a margin of error around there. And we saw that when we know the standard deviation of the box, when we have a known SD, this is what we did here, we had a known sigma, then we use Z, as long as the population isn't too skewed from normal. So with the known sigma, you're never gonna, this is more important to remember, you'll never use T. We're about to start the T distribution and it's kind of confusing to people. So if you know what sigma is, the population in the box, you never use T. Okay, so for example, what we did here, let's say e.g., we have a box that has zeros and ones. Okay? Now, we never use T here because we know sigma pretty close to sigma. Once we get our average, our percentage, our P, percentage of ones in the box, then we can easily compute sigma directly from there. So it's a very good estimate, a very good estimate. So if you have this, a percent problem, basically, then you have almost known sigma and you don't use T. So you have a almost known sigma, so we use Z, not T, if you have a big enough sample. If you don't, you use something, the binomial distribution. But, so you're never going to use T for any of these, if you just have 2 categories like that. Now, when do you use T? So now, when you don't, this is what we're moving into using the T distribution, and there's a different situation when you have an unknown sigma. That's the only time that you'll use T, is if you have an unknown, and not always even. So if you have an unknown sigma, use T. And we're going to see you can use T. If the sample size is large, you can still use Z because of the central limit theorem. So you're really only going to use it when you have an unknown sigma that you have to estimate from your sample. You're going to use this T statistic. And so it's generally when your sample size is small and when you're drawing from a normal population. So use T when population inside the box, here will be your box, has like a normal distribution, and N is small. Then you have to use T. All right, so let's go through, I'm just giving you this rule here, and now let's explain it. All right, so here's an example. Suppose a random sample of 100 females, U of I freshmen, was taken. We wanted to estimate the weight of all 4,000 UI freshmen, okay? And so we take a sample of 100. Now that's pretty big N. That's a pretty big N, all right? And in our sample, we get this average of 135 pounds, and we get a sample standard deviation equal to 25 pounds. So what would you estimate the weight to be? Well, you're going to use this right here to estimate that the weight, if you want, if we had this, now we don't know, we're in this situation where we don't know what's in the whole population, okay? So we have this huge population of what? So our big N, our population size, is 4,000. And in here, imagine that there's 4,000 for our box model tickets, and on each is written what? On each is written the weight. Look how each is written, come on. Each is written a weight in pounds, okay? So, but we don't know what the average is, mu, and we don't know what this population standard deviation is. We don't know either of those things. And this is a much more common situation than we originally started off with in gambling games, where we had a well-defined box and we were looking at the sampling distribution of all the likely possibilities we could get when we randomly drew from it. This is much more likely. All we have is one single sample of 100, and we're trying to estimate these two things. So we're going to use, so what are we going to estimate? To estimate mu, we're just going to use this sample right here. So that's what we'll do here. We'll estimate by our sample, x bar equal to 135 pounds. That's what we're going to put in here. And then, what are we going to do here? What are we going to do with that? Well, first, it said, what are we going to use for the standard error of the sample average? We don't know it, and we really don't know that the population's normal. In fact, it doesn't look, it's somewhat normal, but it's skewed to the right. It's skewed to the right. Most people are like 95%, if it was normal, 95% of the people would be between 2 standard deviations below 85 and 2 standard deviations above this, 180. And I think more of the women are heavier than that and fewer. It's not quite normal. So, but because of the central limit theorem, it's close enough, and we have this big sample size here. What is it? So we're going to draw, we draw from this box just to picture what's going on, and draw randomly, n equals 100 times, we're going to get separate tickets without replacement. And that's where we get these statistics from. Our sample statistics, right? So we have 135 pounds, and our SD of our sample is 25. All right, so we say we're going to use that. That's fine to do. But this standard deviation, let's think, to calculate the standard, what are we trying to do? We're trying to calculate how much, we want to put error bars around that 135. 135, give or take what? Do you think it's going to be, we take 100 people, do you think it's going to be 135, give or take 25 for the average? Do you think we could get an average as low as 105? Do you think we would get an average? Do you really think we could take 100 U of I students and get an average of 105 or an average of 185? No, this standard deviation refers to the individual, the spread in the population, the spread in our sample. It's not this is the standard deviation of our sample, of the 100 tickets in our sample. This isn't our standard error for the average, right? Our standard error for the average, which is like a standard deviation for the average, is going to be much smaller. It will be the standard, it's usually what? The standard deviation of the box, which is sigma, over the square root of n. So now what are we going to put in for this? To calculate this, we need the standard deviation of the box. And what we're going to do is use this standard deviation of the sample as an estimate, just like we did before. Just like we did before. We're not going to adjust it because we have a big enough sample size that that's a pretty good estimate. And we know it's not very skewed. So most people would just use that standard deviation here. Okay, so we'll use that. And so we're going to use this estimate. So we're going to estimate this. by the standard deviation of our sample. Okay, so that's going to, so we're going to put this right here as an estimate, even though it's not going to be necessarily exact. And so that's what we have. We have this over the square root of 100, and we see that the average is much small. The standard deviation for the average, or the standard error for the average, is much smaller by a factor of 100. Doesn't that make sense? The spread in our sample, or in the population, is 25. But when you take a sample of 100, you're going to get really much, much closer to the true average. Okay? So we can't assume. What I did right here is not what software programs are going to do. It's just what software programs are probably going to make an adjustment on this, but it's going to be very, very small adjustment. So we can't assume the sample SD is close to the box SD like we did with 0, 1 boxes. You know, where it's always between, the SD is always between 0 and 0.5, and it's directly tied to the percent. But when the sample size is large enough, this sample SD is a good enough estimate of the population SD for our purposes. Some people, and if you're in any other stats course, you'll probably, because they're usually teaching to the software, you'll probably, what will you do? Instead of doing this, 25 over the square root of 100, you would use the sample standard deviation, and it would end up as 25 over square root of 99. That would be the difference. Instead of 25 over square root of 100, it would end up as 25 over the square root of 99. And we're going to do that. But for now, pedagogically, it's much better to understand that when all we're doing is we're trying to estimate the standard deviation of this. We're trying to estimate the standard deviation here. And instead of, this is a good enough estimate. Well, for small samples, very small samples, it's going to make a difference. But I just want to warn you that you'll see something called S that will be this, a little bit bigger than this. It would be times the square root of 100 over 99. We'll go into that later. But this is pretty good. Okay? So that's the first adjustment. That's the first thing. Okay, now can we use the normal curve, or are we going to have to use this T curve that I'm sure a lot of you have heard about? Let's think about it. Well, when can we use the normal curve? We can use the normal curve when we know what? Anytime we know what's inside the box. Like if we knew the contents of the box, the central limit theorem allows us, when n gets large enough, to use the normal curve. Now, we don't know the contents of the box, right? But we know, excuse me, I think I might have misspoke. If we actually know what's inside the box, you don't have to call on the central limit theorem. Then you can figure out the exact probability histograms, right? And if you don't know what's inside the box, if you could have a really skewed distribution, then with a large enough sample size, the beauty of the central limit theorem says that the sampling distribution of averages and sums and percents will look normal. So no matter how skewed or weird or anything's in the box, the central limit theorem is this extraordinary theorem that allows us to use the normal curve no matter what, okay? With a large enough sample size. Now, that depends on how, if you have a really skewed stuff inside the box, like crazy skewed distribution, it's going to take longer. But something like weights, not very skewed, it's going to be sort of close to normal. The central limit theorem will allow us to use the normal curve. And we don't have to use the T. All right? So we can use the normal curve to build confidence intervals around our estimate because the probability histogram for the average of a large enough number of draws follows the normal curve. And for the purposes of this course, I mean, this is an arbitrary cutoff, but if you have fairly symmetrical distributions, let's just say when we have I'm just drawing the line here at 25. There's no reason to draw it there. I'm just saying for the purposes of this course, to the accuracy we're looking at, let's draw it at 25. Okay? So let's go through this example just with the normal curve, and then we'll do the same exact thing with the t. Okay? So what do we want to do? Do you remember what are we trying to do? We're trying to build these confidence intervals, and we're saying that a 68% confidence interval for what? For the population average is equal to what? It's equal to our sample average, x bar, plus or minus, now the 68% is going to go with a critical value of what? 68% of the normal curve is between what? 1 and -1. So that's 1 times the standard error for the average. That's what we're going to say, 1 times the standard error for the average, for x bar, for the sample average. And so we can do this, and we can say that's our sample average was 135 plus or minus 2.5. So the reason why it's so nice using this normal curve is because you can just get a very good feel, very good approximation just in your head. So that means that we can be 68% sure that the true population average among all freshman U of I students is between 132.5 is the lower limit and 137.5 is the upper limit. Okay? Now, what about a 95% confidence interval for the population average? It would just be x bar plus or minus. Now, how many standard errors do you want to attach to it? Because think about the normal curve. What would be your critical value? 95% in the middle is between what and what? 2. So you said 2 and -2. Isn't 95% of the normal curve between it? Or you could say 1.96 to be more exact. Does everybody understand it's 2 here? That's just because the picture is between 2 and -2 is 95% of the curve. So then we'll say we have 135 pounds plus or minus what? This is 1 times 2.5, and now it's going to be 2 times 2.5. Right? So that will be down to 130 and up to 140. So we could be 95% sure that the true population average is in this range. Doesn't that make more sense than using, because what people do is they mistake this standard deviation, which shows how far an individual is typically off from the average, they use that instead of showing this is how far an average of 100 people is, a sample size of 100 is off from the average. Doesn't that make more sense? This right here. So for one person, yeah, it's 25, just if you took a sample of 1. But if you take a sample of 100 and take the average, you don't get accuracy. It doesn't go down by dividing by 100. It goes down by the square root of 100 by a factor of 10. That's how much more accurate you are, depending on your sample size. All right, now, suppose a random sample of 16. Now we have this small sample, okay? Small sample, and the central limit theorem might not kick in yet. It might be too small a sample. So now we have an unknown, and it was taken to estimate the average weight. Again, we're doing the same problem, but let's say we only had n equals 16, and we get everything the same. Now what are we going to do? Since we have this small sample, we'll say less than or equal to 25, and we have this unknown sigma, right? We should make 2 adjustments. First, with only a sample of 16, this 25 isn't as good an estimate. We can improve this estimate here. It will make some more of a difference, okay? So we should really use what's called the unbiased estimator of the variance. Basically, the idea, so that's the first adjustment. We have to use a different standard deviation. Basically, we have to make it a little bit bigger because remember what we do with this 100, with this 16 people, how are we computing this? Let's say we got that. We'd be taking the deviations from the sample average and not from the true average of the box. It's from the sample average, and so it's likely, if we just did this, since the sample average bounces around, it changes, the numbers around it, the numbers around the deviations around the sample average are going to move with the sample average. So they're going to be the deviations will be slightly smaller on the average than if you took them from the actual average in the box. So you get a standard deviation that's an underestimate. So what we do is, what we'll say is we increase it by, instead of dividing by n, we divide by, when you take the deviations, take their average, instead of dividing by n, you divide by n minus 1. So let's do that. So we're going to calculate this standard error plus. So that is going to be equal to the SD plus over the square root of n. We still have our exact square root of n law, except what we're doing now instead is we are calculating a standard deviation plus. So how do we do that? Well, the standard deviation plus, remember we divided by n minus 1. So when we took the square root, we have a square root of n minus 1 in the denominator. So if we had our regular SD, let's say we had our regular SD, we'd multiply it by the square root of n to get rid of the square root of n in the denominator and replace it with n minus 1. So that's what it would look like. And that simplifies, multiply the denominator and the numerator by 1 over the square root of n, and that simplifies to SD over the square root of n minus 1. So those two things are the same. So basically when we're computing, if we want to make a little bit of adjustment, you're either in another class, you'd probably be given this as your sample right here, as your sample SD, and so you just go ahead and divide by the square root of n. But if you are given this SD, like I'm giving you, then you'll divide by the square root of n minus 1. It ends up the same thing. You're making this a little bigger, which is why I'm putting that little plus there to remind you of what you're doing. So this is 25. Why 25? That's that. Over the square root of 16 minus 1. And I got 6.45. If you didn't do, that's what SE. If you just did the regular one, it would just be what? SE would be 25 over the square root of 16. And that's 6.25. So you can see the difference. That's what we're doing. It's just a little bit bigger. Any questions on that? Raise your hand if you've had this before. I just am curious. I'm assuming most people have. Raise your hand if you've ever heard of the T. Okay, most people have, right? Okay. So now we're going to use this T distribution. So we make this adjustment. Now, we could have made this adjustment back here, right? It would have made less of a difference because we would have said, we would have had 25 over the square. This would have made much less of a difference because you'd have square root of 99, right? We could have done that here. You can do that, gives you a better estimate for the standard deviation. But here's where the big difference comes in, is that, I don't know if you know this, but the distribution of the sample average doesn't follow the normal curve if you have to make this kind of estimate for sigma. If you don't know what the standard deviation is in here, and inside here is normal, if inside here is normal and you know sigma and if you know sigma and you know inside here is normal, you know the average and the standard deviation, even if you took a sample of 1 or 2, it's going to be normal because it's normal in here and you have a good, and you know what the distribution is. But if it's normal inside here and you don't know this, you don't know sigma, then it's actually a beautiful thing you can prove. The sample average follows something called a t-distribution. And if you get in an upper level course, you will prove this. You will show that. And you'll show that there's actually a different distribution. But it wouldn't, in this case, follow that t-distribution. This is why, because you have to have, it depends on it being completely normal in here. When it's completely normal in here, it actually follows a t-distribution. In this case, it's not normal here. So it's unclear which would be the better. This is why I don't like to teach it, always use the t. We use it because the software is doing it. But depending on what you're interested in, it's not necessarily a better estimate. It's a more conservative estimate because you're going to get wider error bars. So I'm trying to teach it to you in a way that's, these rules aren't written in stone. What they're written for is the software. And when you get to a more advanced class, you're not going to have to depend on that software. You're not going to have to press t-test or whatever. You're going to figure out what you want and what's best. And you can easily do a normal distribution or whatever. But the way the intro courses are written is to help you do the software. So you will always see, for this type of problem, unknown sigma, you will always see in R or whatever, or the software to use t, but you don't necessarily, you only for sure have to when you know this is normal inside here, and then it actually has a different distribution. In this case, it doesn't, but okay, so we're going to use the t, though. It's a good idea to use it. So we'll use it. And the main reason it's a good idea and people like it is because it's more conservative, which means that you're not, bragging about getting results or getting results that are really more exact than you really have. So people like to err on the side of, say, hey, I got a lot of error bars here. Statisticians in particular, they don't want to, they never are certain. That's the whole point, right? So you're trying to be cautious. And that's why you use the t most of the time, if you don't even have normality in here. Okay, so we're going to use the t-distribution, and we're going to build a 95% confidence interval for the true population average. Now, why do I not like teaching it so much for intro courses? Because it's complicated. There's a family of t-curves. The normal curve has just one beautiful curve. The t-curves has a whole family of curves depending on your sample size, depending on something called the degrees of freedom. And it has the same form. It's going to have exactly the same form, so you'll have a 95% confidence interval, which is still going to be 135. That's our sample average, right? Plus or minus. But instead of having some z star, we're going to have a critical value of t. And then we are going to use here the standard error plus. Okay? This standard error plus. So it's going to look like this. And our 6, that's what we're going to put down in here. That's our standard error plus for this. All right. Now, let's see. So, what does this t-curve look like? Let's turn the page. And maybe we should really learn about the t before we do the problem, so we can do this first. So, when the sample size is small, using the sample SD to estimate the population SD is not very accurate. And this is true for Z too. This is true even for binomial. I mean, this is true for even if we were doing percent problems. People just don't bother with it because when they just generally just use it with the t. But you can always do this if you don't know the standard deviation of the population. This is a better estimate. You divide by, it's called an unbiased estimate of the variance. It's not even an unbiased estimate of the standard deviation, and depending on what you're interested in, it's not even the best estimate. It depends on what you want to do. But you don't only have to use it for the t. You could use it for anything. Okay, it's likely to be too low, so we use the SD plus instead, where you're dividing through by n minus 1 instead of n. Okay? And you can see as n gets bigger, this gets very close to 1, so it becomes negligible. It becomes, nobody cares about it. Now, here's the adjustment people do care about because we have a different distribution. We have t-curves, and you should use the t-curves because it actually, if you actually have a normal distribution and you don't know the standard deviation of your population, this is the distribution that the sample average follows. So this is key, unknown. Okay, let's highlight that. If you know sigma, never use t. That would be stupid. It's wrong. It's absolutely wrong. Don't use it. Okay, so just use it when sigma is unknown. All right, and we never use t for a 0, 1 box because the SD is very close to being known. When the sample size is small, the difference between the t-curves and the normal curves are more dramatic, and you really should use it. You can still use t with large n, it's just not necessary, but most software programs do it anyway. So if you're in another class or an R, it's even hard to find a z-test for like what we're going to be doing. You have to sort of go to it's not readily available. All right, and the population is close to normally distributed. Another reason why we wouldn't use it for 0, 1 box, it's not normal. Okay, so I tried to use this chart here for you to follow. I don't know if it's helpful or not, but if this is known right here, never use t, okay? If it's unknown, when are you going to use t? You're going to use t when you have a small sample. We could say small sample, a kind of normal distribution. This is kind of an acronym. You could say an unknown sigma, then use t. I made this up because I really don't like teaching the t so early on. And I thought this is like a dirty word. Snut. It sounds like smut, slut. It just sounds ugly to me. And sometimes when I'm teaching students this t too early, I'm trying to do a better job of it. I feel like it gets in the way. Pedagogically, it gets in the way of understanding. So I don't want you to, that's why I want you to just think normal so you understand, and then, because this is much more difficult to use. Okay? Has all these conditions. So, I think it's an adorable curve. I love it. It's very cute. It has a nice, analytic solution. It's very nice. Doesn't take any calculating time. That's why the computers can use it. It's great. It's really, when I first learned it, I thought it was great. But to teach, to teach people just beginning statistics is not good. That's all I'm saying. To get too hung up on it. That's what I mean. All right, so when are we going to use it? So when you have an unknown sigma, if you have a big sample size, the central limit theorem kicks in, so you can use z. There's nothing special about the t. What allows you to do this, they always say the t is robust against normality. What that means is that even if it isn't normal, if it's close to normal, you can use the t. That's true, but what allows that robustness, what allows you to use the t even when you don't have real normality is the central limit theorem. That allows you to use z and therefore t. It's nothing special about t that does that. It's not because of the t distribution, it's because of what allows you to use normality, allows you to use t because t becomes normal in the limit. So yeah, you could use z too. So you could use t or t because of the central limit theorem. So that's why. Now, if you have less than 25, really small sample, it has to be close, it has to be much more normal. So if the population is far from normal, and you have a small sample, we're going to do other things that we're going to see later on. We'll see at the end of the course. We'll do other things. So if it's a really small sample and you don't have a normal distribution, you can't use either of these, Z or T. Okay? And we'll use other methods. So that's the idea. And now let's look at these T curves. Okay, so what do they look like? So now there's two differences that you're going to do. The first one is we're going to use the standard error of the plus. We could do that with Z, we just didn't bother to. We didn't bother to do it. It's not something special about T. You can use this for anything. We just didn't bother to do it. And most people don't. All right, now we use the T curves instead of the normal curve. All right, so let me show you what they look like here. So the normal curve is this one that's the tallest here and has the skinniest. This is the normal one that we're used to. And how do the T's compare? So this one's the normal, okay? Now, the T's, what do they look like? Whoops, this is the normal. Excuse me, this is the normal. This one right here, this is the T. Now you see how the T is flatter in the middle and has much fatter tails. So this is T for a sample size equal to 2. And the degrees of freedom, which we're calling K here, equals 1. So that's this one. So when you have a sample size of 2, is the biggest extreme. You see how much lower it is here? You see how much fatter it is here? You have more area, more uncertainty in the tails. This is the biggest difference between the normal, when you just have a sample size of 2, and you don't know the standard deviation of the box. It actually follows, if you have a normal distribution, it actually follows something looking like normal, but it has much fatter tails. Okay? And now by the time you get to K equals 20, which would be a sample size of 21, so for n equals 21, it's so close that I can't even draw it. You see, they keep getting closer and closer and closer. This right here, so this is n equals 2. This one is n equals 3. We can draw that one. You can see it. That's this one. It's higher in the middle. It's getting closer to normal. And it goes down, and it's a little bit, I can't draw it, but it's not as fat, not quite as fat. Okay? So, let's see. So let's just fill in what we know here. So how are we going to do this? So SE, our usual SE, is equal to SD over the square root of n. And we're going to use this SE plus. So SE plus is equal to SD plus over the square root of n. And that SD plus is called S. You'll see it always as S. That's what you'll see it, which is equal to S over the square root of n. But another way to think about it is if you're given the SD, it's going to be without the S, it's going to be over the square root of n minus 1. Okay? So this is SE plus, and that's the difference. They differ by a factor of the square root of n over square root of either n over n minus 1 square rooted or the opposite, or the reciprocal. All right. And notice that as the sample size increases, the T-curves get closer and closer to the normal curve. All right? So that's really important. As your sample size increases, your degrees of freedom increase, and the T-curves go to the normal curve. In the limit, you can say as n goes to infinity, the limit of the t curve is the normal curve. Okay? And the main difference is that the t curves, and this will help you understand them, have more uncertainty. They have fatter tails. The t curves have fatter tails and are flatter in the middle. So, like if you wanted to do a 95% confidence interval, you'd have to go out further than 1.96, because you're smaller in the middle and you have to go out further. So you're going to get wider confidence intervals for the same, wider intervals for the same 95% confidence interval is going to be narrower. We can zoom in more with a normal curve, and that's why people like the t, because it's more conservative. You're going to have wider error bars. Okay? I think that's pretty much explains it. Let's see if there's anything else. What do these degrees of freedom mean? You're going to see them so much. Oh boy, how can I explain this? Okay, so in these degrees of freedom, these are for the error, or they explain how much variation there is around your model. You're trying to predict an average, and these degrees of freedom refer to the variance around your model. And so how many deviations go into calculating the standard deviation? Maybe that's the best way to describe it. Now, degrees of freedom these are the degrees of freedom for your error terms. Degrees of freedom refer to how many deviations go into calculating the standard deviation. That's a good way to think about it. That's where you can understand the meaning of degrees of freedom, because do you remember do you know what the sum of all the deviations is? Remember, if we sum up all the deviations before we take the absolute value or before we squared them, the sum of all the deviations, you know this, right, is equal to what? If you summed up here, if you took the deviations and you sum them up, what do you get? Some of them are positive, some are negative. What do you get when you sum them up? Always. Always, what do you get? Does anybody know? You always get 0 when you sum up the deviations. That's why we have to square them. We could have taken the absolute value, but you always get 0, okay? You should know that when you're taking your deviations from the average, will always sum to 0, okay? Whenever you take, on your way to the standard deviation, the reason we square them is because if we didn't, they'd sum to 0, right? Okay. If we took their absolute value, that's another way of doing a measure of spread. But we can't just add them up. Now, this degrees of freedom means since the sum of all the deviations is 0, what I mean is the sum of all your x sub I minus x bar from I equals 1 to n is 0. That's all I'm saying here, okay? So if you sum them all up, they're 0. So think about it. If we sum them all up in 0, once we know n minus 1 of the deviations, let's say you summed them up and I told you there were 11 deviations, and I said, I summed up 10 of them and I got -5. Do you know what the last deviation would have to be? It would have to be 5, because the sum of all 11 would have to be 0, right? So once we know n minus 1 deviations, the last one is determined So we say, this is where the degrees of freedom come in. So we say that n minus 1 of the deviations are free to vary, but once you know them, the last one's fixed. It doesn't give you any more information. And that's why you say you have n minus 1 degrees of freedom. But once you know them, so n, this is why the degrees of freedom. The last one's determined. So n minus 1 of the deviations are free to vary. So the degrees of freedom, that's what this stands for. Degrees of freedom are how many of your deviations are free to vary. We call it df is equal to n minus 1. Does that make sense? Not if it makes sense. Okay, so that's the idea with these degrees of freedom. Later on, you're going to be learning other degrees of freedom for the model, but this is for the error. This is the variance around your model. And right now, we're just estimating a mean, so our variance around that mean has n minus 1 degrees of freedom. Okay, so did we do all this? Now that you understand all that, let's finish our problem. Okay, so the standard confidence interval has this form. So now we have to figure out what that is for 95%. So we're going to use the chart at the back of the book. And now I told you there's lots of, it's not easy like the normal, where there's just one normal curve. And if we wanted to find a 95% confidence interval, we'd just go right here. And it's right between 2 and 1.95. It's actually 1.96, but we've just been rounding to 2 because it's an easy number. Now we want to find the 95% confidence interval for the t-table. So this is just showing you here what the way this t-curve is. It just gives you the area of one tail here. Okay? So now we have to look at the degrees of freedom. How many degrees of freedom do we have? Do you know in this example that we had a sample size of what? 16. Didn't we have a sample size of 16? So how many degrees of freedom do you think we have? 15. So we have to look right here for 15 degrees of freedom. So now, what are we going to do? We want a 95% confidence interval. Well, this area, the way this looks, can I zoom out a little bit here? So you can see everything at once? Yeah. Got to get that focus, sorry. Okay, so this is just area of the tail. So here, let's just draw another picture. We want a 95% confidence interval. So a 95% in the middle. So what's going to be on these tails? 2.5 here and 2.5 there. So do you see how this right here matches up to a 95% confidence interval? This gives you this 2 point on the t-curve. It says 2.13, between 2.13 and negative 2.13 on the t, with 15 degrees of freedom, right here, that is our critical, that is T star. So T star right here, with 15 degrees of freedom for a 95% confidence interval. These are the critical values, okay? Does this make sense? So that's for 95% confidence interval, because and this would be what? If it was 1% in the right tail, what confidence interval would this be? What would be in the middle? 1% on each side, so this would be a 98% confidence interval. What would this be? The critical value for a 99% confidence interval, because that's 0.5. This tells you the area here. What would this be? 1.75 would be a t critical value if you had a curve of 15 degrees of freedom for what? 90% confidence interval. This is what? 10% on each tail leaves what in the middle? 80% confidence interval, and it's 1.34. They're always a little bit bigger than the z. And this one would be the 50% confidence interval. And these are the critical values. So we want this one. This is our t star is equal to 2.13 for the 95%. If I wanted a 99% confidence interval, our t star would be that. Does that make sense? Okay, so this, see how it's bigger than the one for the z. We're going to get wider confidence intervals. This is the big difference. We're using a different curve. But as you see, watch what, look, if you only have, look how big they are if you only had 2 degrees of freedom. That would mean a sample size of 3. They'd be giant uncertainty. What would this mean? A sample size of 2. You have a giant, really fat in the tails. Okay? And as you get, it starts getting smaller, getting closer and closer to the z critical values. Okay, so that's pretty much, let's go back, see what else we have to do here. Where are we? Okay. So, whoops. So now we're going to look at that, and we say 135. So our answer is 135 plus or minus 2.13 times what? Times our standard error. So it's going to be 2.13. Let's look at this. Times, so it's 2.13 times 6.45. All right, and so let's draw the picture so you know what you're doing here. So the picture looks like this. And in the middle is 95%. And this is 2.13, and this is negative 2.13, and this is the t curve with 15 degrees of freedom. Okay, how many degrees of freedom? Degrees of freedom is equal to n minus 1, which is 16 minus 1, which is 15. And how does this compare? It's wider. How does the t, it's wider. Confidence intervals are wider using t because t star is bigger than z star. Remember, 2.13 is bigger than 2, or 1.96. Okay, so let's see. So we have to subtract from 135, and I got 121.3 as the lower limit, and 148.7 as the higher one. So that's the idea. Now let's move on, and let's see what we're doing next. Choosing how many people to poll. Okay. All right, so now this is important. Like, let's say a polling organization asked you, how many people should I poll if I want a margin of error of 2% or 3% or whatever? So I just want to get in here a little bit more. Okay, so how would we do these? How would we do these problems? Well, our margin of error is just how much we attach to the wiggle room we attach to our point estimate. And it's just, so the margin of error is just equal to what? Plus or minus, we get some point estimate, and we add plus or minus times z star times some standard error. That's all it is. Now, so if you want to calculate what samples, if you're given that you want a 3% margin of error for a 95% confidence interval, you want to figure out how many people to poll. So all you have to do is then plug this, use your standard error formulas, and solve for n, right? So here's your standard error formula. A margin of error is, for a percent, this standard error is this part. So you just do that, and then, so all I'm doing is, this is the idea. Then you plug in your standard error formula, and then you solve for n. And that's all we're doing here. Okay, so we can do it. In a pre-election poll, in a close race, let's first solve for n. Let's do that. So if we solve for n in the denominator here, we'll get n equals z times, this is z star, times SD divided by the margin of error times 100. That's the square root of n would be that. And then we're just going to square it. And if we were dealing with averages, we do the same thing, right? N is equal to z times SD over the margin of error, but there's no 100, and we'd square it. All right, so now what are we given? In a pre-election poll in a close race, you may say, all right, so here's your 3% margin of error, so we'll say n equals 95% confidence interval. So we'll say that z star, will just approximate it that with 2. What is our standard deviation? We have a close race. A close race means 50-50. So so it would be SD, the maximum SD is 0.5. So to be conservative, we'll use that. And it's very close to that in a close race. So that's times 0.5 for SD times 100 over the margin of error is 3. And then we square that, which is equal to 100 over 3 squared. So it's like 33.3 squared, and it's 1,111.1. And you usually, if it's people you're talking about, you round up. So you round up. If they ask for the nearest integer, round up to that. So that would be your answer. You could give that, but if they ask for an integer, you'd round up. All right, let's try this one. What about a 90% confidence interval? Well, we'll do the same thing. 90%, you'd have to look up the critical value of z. Why are we using z? Because it's a 0-1 box, right? We're using z, and people generally use z for this. So this isn't 2 anymore. It's going to be 90%. Is just going to be, it's less. It's 1.65. How did I get that? I know it, but it's in the back of the book. It's between 1.65 and negative 1.65 is 90%. So you do that times 100 over, whoops, what did I forget? The 0.5. So times 0.5 times 100 over 3, margin of error 3. And then that's 82.5 over 3. So you don't need as many people. I got, what did I get? Boy, I didn't write it down. Hold on, I think I might have written it down somewhere else. anybody have a calculator? 756 point. Thank you so much. So we would round up to 757. All right? So in calculating how many people to poll, we assume the standard deviation to be 0.5, which is, so we don't need as many people if we don't want to be as sure. The more sure you are, the more people, I mean, if you want to be more sure, you're going to have a bigger confidence interval and have more people. Okay, so what if it was only 0.4? When the standard it was really less, how many people would you need to poll? So all we would do is substitute 0.4 in there. And what do we want? A margin of error of 3%, 95. Okay, so we would just say n is equal to 2 times 0.4 times 100 over 3 squared. And that I got 711.1, and you'd round up to that. Now, okay, any questions so far? So what if we had to do one for averages instead? Okay, so for averages instead, it's even easier. So let's say at a grading meeting, what do we have? Assume the standard deviation is 10 points, and we pick a random sample of exams to grade to estimate what the class average will be. How big a sample do we need to get a margin of error of 2 points with 95% confidence? Suppose we had a really big class like Stat 100 that has like 1,500 people. So how many would we have to take out if we were hand grading them and we want to estimate what the average is going to be? This actually is taken from what I used to do. How many would you have to sort of randomly take out? If I wanted to get within 2 points, so I would know ahead of time whether I needed to curve or not. So what would you do? Now you say n is equal to, 95% would say 2. Now we're given the standard deviation. Where is it? Right there. Times 10. Right? Do we have to multiply by 100? No. Over the margin of error, which is what? At the gradient, margin of error of 2 points. So that's there, right? And then we'll square it. And that's 100. So we'd need 100 people. I didn't have to use the 100 here. I'm just using this formula. And if you repeated with 12, then it would just obviously be what? It would be 2 times 12 over 2 squared. So if it's a bigger standard deviation, you'd need more people. So that's pretty easy. Any questions on that? So basically, you can derive it yourself. Just remember, margin of error is that critical value times the standard error. And now, what do we have? How much time do we have left? 10 minutes? All right, let's start hypothesis testing here. Significance testing. I took too long on the t-curve. All right, so this is really important. You're going to see hypothesis tests all the time. You're going to see basically what they are is what? It's a statistical test to see if some effect you see is just due to random chance or if it's if it happened for a reason, due to some particular cause. That's all it is. And so then what you do is, it's called a hypothesis test, and there's lots of different hypothesis tests or significance tests that you're going to see. And what you do is you formulate these two competing hypotheses. One is called the null hypothesis, which is a very dull hypothesis, that whatever effect you see that you're interested in, like did the tree, whatever effect is just due to the luck of the draw, okay? It's just due to, so the effect that you see is just due to chance. The effect we observe some effect, is just due to the luck of the draw. And then you have this alternative hypothesis. So this is abbreviated H naught. This is H alternative. And it says there's something else besides chance that's going on. There's a particular reason. We got this for a reason. So the effect we observe happened for a reason. It's not due to the luck of the draw. And people like to prove the alternative. They always want to, something happened for a reason. So it's the null is sort of generally the hypothesis of no effect. It's the dull one. Like, yeah, the treatment didn't really work. It's just due to random chance. If we repeated this over and over again, you wouldn't see this. And the alternative is, no, it did work. We wouldn't see such a big difference just due to, that's too big to be due to the luck of the draw. It has to be it's due to something else. We don't get that kind of difference just due to chance. So you argue by contradiction. You assume the null. You assume it was just due to chance, and you assume it's due to the luck of the draw, and then you build a box model that's an analogous box model that is the luck of the draw. That's all you do. So you assume it's due to luck. You assume effect is due to luck of the draw. So you make a box model, a probability model, and see, okay, how likely is it that we'd get this big an effect just by the luck of the draw? So what do? You will ask if the results you found are very surprising. If it was really drawn from that box, we create a probability model. A box model. And we say, okay, we're going to create this luck of the draw. How likely is it to get this effect as big as what we saw? So we have to pick this statistic that you'd expect to be different for the null and the alternative hypothesis. And you pick some test statistic that has a known sampling distribution, like Z. So you pick a test statistic, like Z. For example, Z, that's not the only one. We're going to T, chi-squared, there's tons of them. But you pick a test statistic, for example, a Z-test, we'll do that first, with a known sampling distribution. So when you randomly draw from that box with the known sampling, you know the likelihood of getting an effect as large as you got just by the luck of the draw. For example, the mean. You could do, and then Z would be like what you observe minus what you expect over some standard error. So you could say, okay, I observed this mean, I expected some other mean over the standard error for the mean, and then you can draw the sampling distribution, a normal curve, and see how likely it is that you got that far from what you expect. That's called the p-value. So basically it looks like this. You have some sampling distribution like this of your test statistic, and this is the under the null, assuming H naught under the null. This will be your sampling distribution of your test stat. Let's say your test stat was this one, Z. Okay, so what do? So this is what you'd expect to get, like right in the middle. And then you say, okay, how far from that did I get? How far away? And if you got too far away, at some point you have this null cutoff, which is called, they usually set it at 5%. It's called alpha, the significance level. And that is equal to your null cutoff. So you say, this is how they all work, these significance tests. So you say, okay, this is what I expect under the null. This is what I observe after you change it into a test statistic. And then you say, okay, this isn't what I observed. I observed comes somewhere here. The difference between those, this is like the cutoff for decision maker. So, you put if your observed thing is way out here, let's say your observed is way out here, it's too far out here, you reject the null. You say, it's not just due to the luck of the draw. you would reject the null. And this right here is generally set at 5%. That's sort of a convention. You can set it at anything you want, but generally this area is 5%. So if there's like a 5% chance when the null is true, this is 5%, this is 95%. And you measure how far your observed is from what you expect once you translate it into into a z-score. So if your observed is on this side of it, you'll say you reject the null. If it's here, you say, could have just happened by chance. It's like our jury system. This is beyond a reasonable doubt. We assume innocence, nothing particular is going on, the null dull thing, just an ordinary citizen. You get enough evidence against him, he's over here, and it's beyond that reasonable doubt. That's called the null cutoff. How low is low? The convention is to when it's less than 5%, sometimes less than 1%, it's called highly significant. So that's the idea. Can we start, I guess, we could start one example. How much time do I have? Like 2 minutes? Literally 2 minutes? Aw, darn. I didn't get very far. I was supposed to cover this. Shoot, I can set it up. All right, so this is a real life story. Let's say that we had 1,000 students, and on a midterm exam, the class average was 70. So we have this box with 1,000 students, 1,000 tickets, and this true story sort of, so mu is 70, all right? And I also knew that the standard deviation sigma was 12. And then there was this one class that I assumed ahead of time, early morning class, that had a much higher average. And ahead of time I was thinking, that class is going to do better. So you want to know, is that 5-point difference between the observed minus the expected, between the 75 that class got early morning minus the 70 just due to chance? There were 36 sections or 27 sections, something like that. One of them's going to do better just by chance. How likely is it that you'd get that big a difference just by chance? Null hypothesis, it's just due to chance variation. Alternative, there's something different about those early morning kids. So you say, let's just say, set up a box model under the null. Let's say if we really randomly drew n equals, how many students are in that class? N equals, this is this, n equals 36, n equals 36 students. How likely is it to get, and there we got an average of 75. Is that 5-point difference real or just due to the luck of the draw? So you'd say set up z is your observed average minus your expected average over the standard error for the average. So z is equal to your observed sample average minus what you'd expect over your standard error for the average. And that is SD over root n, which is 12 over the square root of 36, which is 2. So you get 75 minus 70 over 2, which is 2.5. So you say, by the luck of the draw, we know the sampling distribution of the average looks like this, the normal curve. And we'd say, okay, we'd expect 70 right in the middle. How far out is 75? How far out is it? Where do you think? Do you think it's way out here? You think it's in here? You don't know until you change it to a z-score and you see exactly where it is. It's at 2.5. So between 2.5 and negative 2.5, that's where 75 is. So that 5-point difference turns out to be enormous because right in the middle here is something like 99, I think I have to, 98.76%. So our p-value is just that tiny area here, which is 100 minus 98.76 over 2. So we get this tiny 0.62%. So well beyond our cutoff of 5%. So we would say this wasn't just due to chance. The chance that it would be just by the luck of the draw is less than 1%. So that's the hypothesis test in the nutshell. It's pretty simple. But I'll talk about it more later. So this is our p-value. That's our p-value. So p is equal to 0.62%. And what would you conclude? You'd say, since p is equal to 0.62%, which is less than 1%, the result is highly significant. The result is highly significant. So we'd reject the null, that it was just due to luck, and conclude there's a reason for it. And conclude it wasn't just chance. The difference, the 5-point difference in averages is not just due to chance. Because if it was due to chance, we'd only see it. It's not like, yeah, we'd see it once in a blue moon, only less than 1% of the time. So that's the idea of the hypothesis test. It's just saying you're just testing two hypotheses. The null is always just due to chance, and the alternative is due to some reason, something besides chance. And then you set up a chance model, probability model, and you see how likely it is. Sorry I rushed through it. Did you understand it? I probably was clearest on that because I went fastest, right? It's because when you go faster, sometimes it makes more the t distribution is just hard to explain. Significance testing p-values is easy. It's just logic. Okay, the t is just a mess to explain. And I spent way too much time, but I'm glad this is what you really need to know, the hypothesis testing. So I'm glad you understood that. Thanks.